Assalamu alaikum, my name is Amashmas. You're watching my YouTube channel, and welcome back to the second series of lectures in which we are simulating green ammonia in Aspen HYSYS. This is the last video in which we will see that how we can simulate the refrigeration cycle in Aspen HYSYS. And in the last video, we have performed the heat integration and designed the heat exchanger network because we have to decrease the temperature of the effluent stream that was 483 at the reactor out, and for the separation of ammonia that was generated, we have to decrease its temperature. So we have used a series of heat exchangers and decrease the temperature from 483 to here you can see that up till 303 degree for the separation of ammonia. And the unreacted gases have been recycled back, and this is the liquid ammonia. Now we will see that how we can simulate the refrigeration cycle in Aspen HYSYS for ammonia liquefaction. So let's see. First of all, after this ammonia liquefaction, we will use a so the first thing is to decrease the temperature of this liquid ammonia because you can see that its temperature is very high. So I will go to my model palette, and here from the pressure changers, where these are the pressure changers, I will select a valve, and this valve will act as a let down valve. So I will make my connections. Its inlet will be liquid ammonia, and here you can write as let down ammonia. So that's good. I will go to the worksheet, and here I have to specify the pressure. So here I can specify my pressure at the downstream of the let down valve is as 25 kg. So now that's good to go. Now you can see that it has been converged. So after that, now as we have seen that the ammonia that was present over here was having small amount of nitrogen and hydrogen in it. So we have let down the pressure, and now we will again use a separating drum over here, and the small amount of nitrogen and hydrogen will leave from the top, and we will also, and from the bottom we will get the pure ammonia that will lead to the refrigeration cycle. So again I will go to the separators here. This is my separation drum, so I will place it over here, double click on it, and my inlet will be liquid ammonia. My bottom stream will be my bottom stream will be the ammonia that will be ammonia, or you can set ammonia to refrigeration. On a refrigeration cycle, top you can write as waste, or you can name also as purge stream. Purge. So that's good. So now you can see that my simulation has been solved. So that's good. So now this ammonia, so now this stream will be the inlet for our refrigeration cycle. So here I can, so the first thing here I can, to start with, first of all, I will add a splitter over here, and this is a T. I will place this T over here, and I will let me. So I will place a T over here. I can change its direction to rotate horizontal. So now here you can double click on it, and now its inlet stream will be my ammonia to refrigeration. So now why I have used a T over here or a splitter, because if you want some of your ammonia that you do not want to go to the refrigeration cycle, so you can separate some ammonia over here. So you can write as here as spare, spare I can add, and this ammonia will be going to our chillers. These chillers will act as evaporators. So as an initial simulation, I will place a large value over here because I want a large flow of ammonia in the chiller so that I can converge my the heat exchangers that are still not converged. So here I can write as two chillers, and after the chillers here I will again use a T over here, and or you can say a splitter. I can split it horizontally and I double click on it. So after double click on it, its inlet will be two chillers. So if I go back to my heat exchangers, let me close this. So here these are the two heat exchangers. So now here one this heat exchanger will be my high pressure chiller and this will be my low pressure chiller. So I for this I will double click on it and I will rename my two streams. That one will be high pressure chiller in and the other will be my low pressure chiller in. So that is good. So now again I have to specify my split ratios. So here you can as an addition, because in high pressure chiller the temperature change is from 40 to 11 degrees I think. So I will give a larger flow over here, so I can give as 1500 kgs to this high pressure chiller. So now what we will be doing after this? So these chillers are actually kettle type reboilers, but for simulation in Aspen HYSYS, you have to use let down valves to decrease the pressure. So here I will use a let down valve. So first of all, I will change the direction of my screen so I can rotate it. So again, so that is good. So now I can place it over here. So now here I will go to my model sheet and I will place again, I will again take two valves. One will be my let down valve for this low pressure and one will be my low pressure let down valve for this high pressure stream. So again I can rotate it. So that is good. So I will double click on it. Its inlet will be, so if I drag it a little down, its inlet would be low pressure. So here you can write as low pressure chiller. One you can write as, or you can write as heat exchanger heat X. So that is good. You have to specify. I will cross it. So I will double click on it again, and from the worksheet, I will define its outlet pressure. For the low pressure, you can decrease the pressure up to 200 kilopascal or in the range of 200 and 300 kilopascal. So I am decreasing its pressure up till 200 kilopascal. So if I now I will double click on this my heat exchanger, and here you can I will go to the design, and in the shell what was my inlet? My inlet is low pressure chiller heat exchanger in. So that will be my inlet, and my outlet will be low pressure chiller heat X out. So that is good. So now you can see that my simulation has been solved. I will go to the worksheet. So now you can see that a very small change in temperature is happening. So you can, if you want, you can increase the temperature over here of let down to 250 kilopascal. So now you can see that your temperature is increased, and now the delta T is minus 13 and 3. You can say 15 degrees, 15 to 16 degrees delta T is present. So that is good. So now it is good. After that, now I will converge my this high pressure chiller. So for high pressure chiller, again you place the valve over here. I will rotate it. So that's good. Double click on this. No, sorry. Double click on this heat exchanger. Oh, sorry. Valve. Its inlet will be high pressure in. So you can write that its outlet stream as high pressure chiller heat X in. So that is good. So now again go to the worksheet for the high pressure. You can take pressure around from 400 to 500 kilopascal. So I am taking as the initial as 400 kilopascal, my initial. So that is good. And now you can double click on it, and for the shell side, my inlet is this one, and my outlet will be high pressure chiller heat exchanger out. So that is good. So now again my chiller has been converged. I will go, and here you can see that around 13 to 14 degrees delta D is present. If I increase this pressure to 450, so you can see that my till 450 is also good. But if I increase this pressure up till 500 or more than 500, then these two temperatures will be approaching in each other, and then you will be having an error over here. 450 degrees is good. So now you can see that I have converged all my heat exchangers. So here what we have done up till this 40 degrees, because with the cooling water we can decrease the temperature of the stream up till only 40 degrees. After 40 degrees we have used our low pressure ammonia, and with the decreased pressure, when you see that when you will decrease the pressure of a stream, its temperature also decreases, like as it happens in Joule-Thomson effect. If you adiabatic expansion cause cooling, so this expansion is happening over there, and your stream is cooling. And so now after this, what we will be doing that after each this high pressure chiller out and low pressure chiller out, we will be using two separators, and we will separate out the liquid and the vapor streams. And after this liquid stream, that liquid stream will be heading towards a atmospheric drum, and where in the atmospheric drum we will decrease the temperature to approximately atmospheric temperature, and after that the liquefied ammonia will be heading towards the storage, and the vapors from that atmospheric drums and from the high pressure and low pressure atmospheric drum will be heading towards the compressor, and after compressor we will use a condenser that will reject the heat. We will use a condenser, and after the condenser we will send back our stream, the compressed stream to over here, and then our loop will be happening in the total recycle. So we will see that how we will be doing that as well. So I will come to over here, and here I will again go to my model palette, and I will select here as two separating drums. One will be for my low pressure, and the other will be for my high pressure stream. The outlet streams from the high pressure chiller and the low pressure chiller will be the inlet for these two drums. So I can rotate horizontal both these drums so that the traction will not be reversed. So it will be our low pressure drum. So I can name as its LP drum. So that is good. And my inlets, its inlets stream will be low pressure chiller heat X out. So that is good. So that will be my, you can write as booster LP out to booster compressor. So LP out to booster compressor. So that is good. And this string will be going to, you can say, LP to atmospheric drum. So that is good. So you can see that this drum has also been converged. So after that, I can rotate its direction. So that is good. That is good. So now I will go to this drum, and here my inlet stream will again be this will be my high pressure heat X out. I can rename as high pressure drum. That is good. You can write as high pressure out to booster compressor. So that is again from the liquid outlet. You can send this liquid out. We will send this liquid out to atmospheric drum. So high pressure to atmospheric drum. So that is also good. So now you can see that I have. Uh, so now I will again change the direction of multi-stream. So that is good. So now these two vapor stream will be the inlet of our compressors, booster compressor. That will boost pressure to 25 kg, and then we will be recycling back to our main drum from which we have taken out liquid ammonia. So that is good. And now these two streams will be going to our atmospheric drum. Go to my model palette, and from the model palette select mixer, double click on it. Inlet streams are if I make it, if I drag it a little bit down. So first stream is high pressure. So this is not high pressure to atmospheric drum. And so sorry, I have selected a T over here. So I will delete it. Again, go to my model palette, and from here I will select a. This is a mixer, and this is a mixer. So this is a mixer. I will double click on it, rotate horizontally. So that is good. Double click on it. So now I will inlet HP to atmospheric drum, and the other will be LP to atmospheric drum. So that is the LP to atmospheric drum. Out, you can write as inlet to atmospheric drum. Okay, that's also converged. So now here we will again be using a letdown valve, and from this letdown valve we will be decreasing the temperature to 100 kilopascal. So again I will go to the model palette, and here from here I will select again a valve. This is our last letdown valve, and from here I will double click on it and inlet to atmospheric drum, and you can write here as final inlet to atmospheric drum. So that's good. After that, it will say that what will be my outlet pressure. So outlet pressure you can write as 100 kilopascal. So now here I will make a little bit of changes to its direction. So now it is good. I will. So now this is the final drum, that is the atmospheric drum. So again I will go to my this model palette, and from here I will place a drum, that is my last drum, and it is my atmospheric drum. I will double click on it, and so now here final inlet to atmospheric drum, and this is my atmospheric. So you can write as two atmospheric drum to booster compressor. Okay, so that is my final ammonia, liquid ammonia to storage tank. So now you can see that this drum has also been converged. So if I double click on it and go to the worksheet, these are not the actual values. When we will get the actual values, once we will recycle our these three streams, this one, and low pressure stream, after increasing their pressure back to the drum from which the liquid ammonia was being obtained. So again, I will make a little bit of cosmetic changes. So this make it a little bit that in this way. So this is my final liquid ammonia. So that is good. So now after this, I will place a mixer over here. So this will be my last mixer Hopefully it will be my last mixer. So again, this is a T, this is a mixer. So I will place it over here, or you can place it over here. So give its inlet streams. Inlet streams are three streams. First of all will be low pressure, high pressure out PC. Second one will be low pressure, low pressure out PC, low pressure out PC. So this is low pressure out PC. And its third stream will be the atmospheric drum to PC. So that is the third. So now you can see that all of three has been added to my this mixer. And now what I am going to what so now what I'm going to do, I'm just adding all my these low pressure streams to a booster compressor, and from that booster compressor, after increasing the pressure to 25 kg, I will send, I will recycle back all these streams to our main drum from which liquid ammonia was, we was obtaining liquid ammonia. So you can write as inlet to booster compressor. So that is good. So now here you can use booster compressors. So I will double click on it and see that. So now we will simulate our say compressor. Compressor you can on for the simulation sake you can just I can just place a simple compressor over here and increase the pressure from 100 to 25 kg, 100 kilopascal to 25 kg. But but actually this doesn't happen like this. We have to select the compression ratios and stages, and then periodically increase the temperature, increase the pressure to 25 kg. So I will be doing that. Uh, so here, first of all, I will take my first compressor. That will be my interstage cooler heater. So, but I am taking three compressors with compression ratio of 2.96, and see that after the third compressor stage, my after the third compressor stage, my pressure becomes equal to 25 kg or not. So I will simulate this first. I will show that how we can do this only first stage, and then I will increase the speed to simulate my two compressors. So first of all, you can its inlet will be my this one. So it is inlet to my booster compressor, inlet to booster compressor. Here you can write as booster compressor 1 out. So that is good. Here you can write as booster compressor energy. So that is also good. So now go to these parameters, and here select the compression ratio. So this is the pressure ratio 2.96. 2.96. So that is good. So now here, if I double click on my compressor, uh, so if I now double click on my compressor, go to the worksheet. So here you can see temperature is increased to 93. So we will use an intercooler. So this intercooler will be used to decrease the temperature to these intercoolers are having generally water as their cooling media. So I can decrease the temperature up to 45 degrees. So BC1 out. Here you can write as BC2 in, and here you can write as BC booster compressor 1 heat or intercooler heat. So that is good. So now go to these parameters. So I have given my delta P as 0 in this my whole solution. I haven't give pressure drop at any place. So here I can write as outlet temperature 45. So now I will be doing the same with the other two compressors also. So just I will be now increasing the speed of the video and quickly doing and quickly simulating the other two compressors. So now you can see that this was my last compressor. So I will double click on the worksheet. So go to my worksheet, and here you can see that my pressure is a little greater than the required one. So I will can double click on that and go to my this design, and from design here I can delete my compression ratio, and from the worksheet I can write as my outlet pressure as 25 kg. So sorry, this is not my pressure. So here, so now here I will specify my outlet pressure as 25 kg, 25 kg per centimeter square. So that is good. So now again I can go to my design parameters, and it's in the last compressor the compression ratio will be 2.79. So I have just done some back calculation or some. So now this heat exchanger or this cooler will act as my condenser. So you can write here as condenser, and after this condenser I will be recycling that my vapors back to the ammonia drum, ammonia liquid drum. So that is my inlet will be B3 out, and recycle liquid ammonia. So that is good. Heat exchanger you can write as condenser E. So I can write as condenser energy. Parameters you can give as pressure drop 0, for the outlet pressure, oh sorry, outlet temperature, you can give as 30 degrees, or you can give a 32 degrees. So now that is good to go. As now we are recycling this stream back, so we will be using our recycle function over here. So I will place this recycle over here. I will double click on it. Its inlet will be my recycle, that one. So if I outlet will be recycle to liquid ammonia 1. So this has also been solved. So I can rotate it and rotate it like this. So now this is the stream that I will be using. So if I drag it a little to above. So now we will be dragging this recycle stream back to the original drum from where the liquid ammonia we were getting our liquid ammonia. So that was the main drum from which the liquid ammonia we were getting. So I will double click on it, and that is our stream, and we will be recycling that stream back to our this main drum. So just so that is my main stream. So now you can see that this stream is also converged. So now you can see that my this drum has been converged. That's all for the simulation. We will see that either something is unconverged after our simulation. So you can see that our this high pressure heat exchanger is unconverged. Yes. So we have to increase the flow. So here, come here, and out of this splitter, you can increase the flow to our chillers. So what was, you can increase the flow to 20, first of all 2400. So 2400. So now we will see that either it is converged or not. So now here it is still unconverged. So double click on it and see that. So here, go to here, and from here you can increase the flow rate to our this heat exchanger 17 method. So now you can see that now it has been converged. So now we can see that other thing, either some of the thing is unconverged, so nothing is unconverged. So I will double click. So here, so you can double click onto my atmospheric drum and see that. So now it is also converged, and from this you can see that 88 tons per day of ammonia is going to our storage tank. And you can manipulate the values of the splitters and the flow that you want to bring in and out to those evaporators, and you can decrease or increase the ammonia flow. So that's all for that, because here you can, if I open this spare stream, so here this spare stream is having a large amount flow, 908 ton is flowing into it. So if you increase the flow towards these chillers, you can increase the flow towards these chillers. So if you increase the flow over here, so now then there will be low flow over here, and when there will be low flow at this place, so your ammonia liquefaction will increase. So now you can see that that is my whole simulation for the simulation of green ammonia. If I make it a little bit smaller, so you can see that this was the, so after booster compressor, this was our high pressure and low pressure drums. This was our atmospheric drum, and this was all part of our refrigeration loop. This was our integration network to reduce the temperature of this effluent stream or at the downstream of reactor from 469 or 480 to 3 degrees for the separation of ammonia and the unconverted hydrogen and nitrogen. So this was our, you can see that these compressors are our syn compressors where we have increased the temperature from 580 kilopascal to 215 kg or 220 at atmosphere, around 220 kgs for our to meet our reaction conditions. And this is our electrolysis of hydrogen. And at the bottom we have simulated the cryogenic liquefaction of air for the separation of or for getting the nitrogen stream. So that's all for this video. If I fit it to stream, so you can say my whole simulation will look like this. So if I increase its visibility, so this is the complete green ammonia simulation in this one. I hope you like the video. Inshallah, meet you in another series of videos. Assalamu alaikum.